In the vast expanse of interstellar space, in early August 2023, one of the most distant human-made objects from Earth continued its solitary journey. This spacecraft, like a wanderer lost in the cosmos, persistently sent signals towards distant Earth, desperately trying to convey its operational status and readiness for further communication. But its pleas went unheard. As it turned out, in late July, specialists managing the Voyager 2 spacecraft made an unfortunate oversight. While sending routine commands, they inadvertently altered the antenna's settings, causing it to deviate slightly from Earth. At the colossal distance separating the spacecraft from our planet, even the slightest change in antenna position can result in complete loss of communication, making it impossible not only to control the spacecraft but also to receive valuable scientific data. However, the story of Voyager 2 did not end tragically. On August 1st, something incredible happened. Using the extensive network of radio antennas known as the Deep Space Network, specialists detected a faint signal reaching Earth from the depths of space. Although the signal itself contained no useful information, it served as an encouraging confirmation that Voyager was still alive. The culmination came on August 4th, when a powerful 70-meter radio antenna near Canberra, Australia, sent a signal with reorientation commands towards the spacecraft. After 18.5 hours of waiting, the signal reached Voyager, and another 18.5 hours later, a return signal was detected on Earth, indicating successful execution of the commands. The legendary spacecraft, which revealed the astonishing worlds of Uranus and Neptune to humanity, will continue its mission, sending valuable data about the properties of interstellar space beyond our Sun's heliosphere for at least another 3 years. Its sibling, Voyager 1, is expected to operate until 2030, after which it will continue its silent journey alone. The Deep Space Network, DSN, is one of the fundamental pillars in the exploration of the universe, often undeservedly overlooked. It is thanks to this complex system of antennas that NASA maintains communication with Mars rovers, telescopes located at Lagrange points, and even spacecraft in interstellar space. In particular, the DSN allows the James Webb Space Telescope to transmit gigabytes of images of distant galaxies and nebulae to Earth. The aforementioned antenna near Canberra is just one of 3 key communication complexes forming the Deep Space Network. In addition to Australia, large radio antenna complexes are located in Europe, near Madrid, and in North America, at the Goldstone Observatory in California. This international project, managed by NASA, is designed for controlling and operating uncrewed deep space missions. Each complex is equipped with a 70-meter diameter antenna, as well as several smaller antennas. Together, they form the largest and most sensitive telecommunications system in the world. Beyond exchanging data with numerous spacecraft and telescopes, the DSN is also used in radio astronomy and is an important tool for studying the solar system and other cosmic objects. For example, the DSS-14 antenna located in Goldstone is a fully steerable radar system, making it an indispensable tool for observing near-Earth asteroids and comets. Operating in radar mode, the antenna can send radio signals towards asteroids, and based on the reflected signals, astronomers create detailed maps of these celestial bodies' surfaces. The network is also widely used during radio experiments conducted as part of most deep space missions. For instance, the Juno spacecraft, orbiting Jupiter, serves as a kind of indicator for determining the giant planet's internal structure. During the spacecraft's closest approach to Jupiter, changes in the density of matter within the planet caused Juno to oscillate. Using the Deep Space Network, scientists can precisely measure these oscillations and calculate the distribution of matter density inside the planet, revealing the secrets the gas giant hides beneath its thick atmosphere. Primarily, the DSN is a deep space communication system, though not the only one of its kind. The Japanese and Indian space agencies also have their own communication systems, albeit on a smaller scale. The Japanese system consists of just one 64-meter antenna located in Saku. The European Space Agency boasts 3 complexes located in Spain, Australia, and Argentina, but each of these complexes is equipped with only a single 35-meter antenna. Thus, NASA's Deep Space Network surpasses similar systems in scale and power, and can simultaneously support communication with a larger number of spacecraft. As a result, DSN antennas are often used by other space agencies through international cooperation. The strategic importance of the Deep Space Network's DSN-3 complexes is evident. Their longitudinal placement at approximately 120-degree intervals ensures uniform coverage across all 360 degrees of the globe. This configuration allows for continuous communication with spacecraft located at significant distances from Earth, effectively solving the problem associated with our planet's rotation. When one complex loses a signal as a spacecraft dips below the horizon, another takes over, ensuring uninterrupted data transmission. The DSN's history began in January 1958. The Jet Propulsion Laboratory, JPL, which serves as the control center for all NASA robotic missions, was then part of the U.S. Armed Forces. The first American satellite, Explorer 1, transmitted its signals through a network of portable antennas located in Nigeria, Singapore, and California. However, after JPL transitioned to NASA's management and numerous robotic missions began, it became clear that creating separate communication networks for each spacecraft was impractical. There arose a need for a unified, large-scale system to communicate with all missions. Thus, the DSN was born. Since NASA's research center is in California, it's no surprise that the network's first antenna was built nearby in the Mojave Desert in 1958. This location was chosen due to the absence of terrestrial radio interference, which is critically important for receiving weak signals from distant spacecraft. The Australian and Madrid complexes were commissioned in 1965, following the same logic. The name, Deep Space Network, is well justified. Most spacecraft launched into space orbit Earth and low Earth orbit. Various ground stations and communication satellites are used to communicate with them. However, maintaining communication with spacecraft in deep space requires much more powerful and sensitive equipment. The term, deep space, does not have a strict definition. The International Telecommunication Union defines deep space as anything beyond 2 million kilometers from Earth, i.e., beyond the second Lagrange point, where, for example, the James Webb Space Telescope is currently located. Nevertheless, the DSN was designed to communicate with spacecraft beyond geosynchronous orbit, where a satellite completes a full orbit around Earth in 24 hours, remaining almost at the same point in the sky. As infographics show, the DSN antennas provide full sky coverage starting at a distance of about 30,000 kilometers above Earth's surface. For comparison, the Moon is 10 times farther. This is deep space, at least for this communication network. In its first month of operation, the DSN provided communication with 3 spacecraft. Today, that number exceeds 4 dozen, including international missions. NASA provides real-time tracking of which spacecraft are currently in communication. For instance, at the time of writing, the largest antenna at the Australian complex was receiving signals from Voyager 1, the most distant spacecraft from Earth. It can also be seen that one of the antennas in Madrid is simultaneously receiving signals from 3 missions orbiting Mars: Mars Express, Mars Odyssey, and Maven. A question arises: how do spacecraft transmit data to Earth without having antennas as large as those of the DSN? To reduce cost and weight, communication equipment on spacecraft typically has very low power, around 20 watts, like a refrigerator light bulb. As a signal propagates through space, its power diminishes to extremely low values, reaching Earth with no more than a billionth of a watt. Capturing and decoding such a signal is an incredibly complex technical challenge. DSN antennas are equipped with amplifiers, but this doesn't solve all problems. First, amplifiers amplify not only the useful signal but also radio noise emitted by almost all objects in the universe, including Earth and the Sun. Second, the signal amplification equipment itself creates its own radio interference. To address these issues, the DSN uses sophisticated technologies, including cooling amplifiers to temperatures just a few degrees above absolute zero. This allows for the reception of extremely faint signals from distant spacecraft. Additionally, these signals are specially encoded to distinguish them from other radio sources. The DSN antenna's extremely high sensitivity has repeatedly saved spacecraft in emergency situations when their signal strength was significantly limited. For example, during the Apollo 13 mission, limited battery power and the inability to use the high-gain antenna meant the crew could not communicate with NASA's mission control. In this situation, the largest and most sensitive DSN antennas, along with the Parkes radio telescope, played a crucial role in bringing the astronauts back to Earth. Let's consider the process of information exchange between Earth and the James Webb Space Telescope, located at an impressive distance of 1.5 million kilometers from our planet. It's important to note that communication with Webb is not arbitrary. It requires meticulous planning. Each mission receives a specific window for data transmission and reception, taking into account the spacecraft's position in space. Often, there is competition for communication resources when multiple missions simultaneously request access. In such cases, mission teams negotiate to coordinate communication schedules. James Webb communicates with Earth an average of 2 to 3 times per day, with each session lasting several hours. Various radio frequency bands are used for communication, including S-band and Ka-band. The S-band, with a frequency of 2 to 4 GHz, wavelength 10 to 15 centimeters, is technically simpler but offers limited bandwidth, 16 to 40 kbps. It is used for sending commands to the observatory and monitoring its status. The Ka-band, conversely, provides a much higher data transfer rate. With a frequency of about 30 GHz, wavelength 1 centimeter, it allows scientific data to be transmitted to Earth at approximately 28 megabits per second. This enables the telescope to transmit tens of gigabytes of valuable scientific information within a few hours of communication. Using the S-band for this purpose would take many days. James Webb is equipped with 2 antennas designed for different frequency bands. A larger 60-centimeter high-gain antenna is used for Ka-band communication, facilitating the transmission of scientific data. A smaller, medium-gain antenna serves for S-band communication. Both antennas can operate simultaneously, allowing for continuous contact with mission control and transmission of scientific data even during observations. Since James Webb is not in constant communication with Earth, it must store collected data. For this purpose, it has a 65 GB SSD, with 3% reserved for telemetry and engineering data, leaving 58.8 GB for scientific activities. While modern smartphones and computers boast significantly larger memory capacities, this limited storage is likely due to the high reliability and radiation hardening requirements for space equipment, as well as the telescope's development timeline. Perhaps 60 GB seemed sufficient 2 decades ago. This limitation necessitates meticulous planning of scientific observations and communication sessions to ensure the telescope can transmit data to Earth in a timely manner. Webb's operators request 4 hours of DSN time to downlink its data and minimize the risk of data loss. However, this is becoming increasingly challenging as numerous other missions also require DSN resources. The growing number of spacecraft is placing a significant strain on the deep space network. The Artemis mission, in particular, is impacting DSN resource availability. The uncrewed Orion spacecraft during the Artemis I mission utilized 903 hours of DSN operations, while 8 CubeSats launched alongside it consumed an additional 871 hours. As a result, scientific missions relying on DSN lost approximately 1,600 hours of communication time. Even the James Webb Space Telescope lost 185 hours of communication with Earth, according to a NASA audit. The system is becoming overloaded due to the increasing number of crewed and robotic missions, and demand is projected to exceed DSN's capabilities by 50%. NASA is undertaking efforts to address this issue, including constructing new antennas and upgrading existing infrastructure. However, the agency appears to be struggling to keep pace with the rising demand and is exceeding its budget for these initiatives. In an effort to expand the horizons of lunar exploration, the construction of 6 additional antennas is planned. These measures are intended to alleviate the communication burden. However, even with their commissioning, the problem of communication time scarcity between spacecraft and Earth will remain relevant. Nevertheless, a promising solution looms on the horizon. NASA is actively exploring the possibility of transitioning from traditional radio frequency communication systems to advanced laser or optical communication. This technological leap could increase system bandwidth by an impressive 10 to 100 times. As a result, numerous research missions will be able to significantly reduce the time spent maintaining communication with Earth and transmitting valuable scientific data. As a pioneer in this field, NASA's Deep Space Optical Communications (DSOC) experiment will demonstrate the capabilities of optical communication between a spacecraft and Earth. This demonstration will be part of the Psyche mission, heading to the eponymous iron asteroid located in the vastness of the solar system. The spacecraft, scheduled for launch in October of this year, will be equipped with a near-infrared laser transmitter. This device will allow scientific data to be transmitted to Earth at unprecedented speeds. Additionally, the spacecraft will feature a highly sensitive camera designed to receive a laser beam emitted from Earth. Ground infrastructure also plays a key role in this experiment. A powerful near-infrared laser, installed at a jet propulsion laboratory facility located in the scenic Table Mountain area of California, will be responsible for transmitting commands to the spacecraft. Data sent by Psyche to Earth will be received by the 5-meter Hale optical telescope at the California Institute of Technology's Palomar Observatory. Although the optical communication system has undergone preliminary testing, this will be its first application in a deep space mission. If successful, this experiment will usher in a new era of rapid data transmission from future missions to Mars and beyond, marking a significant step forward in space exploration.